So first, we'll start off with a bit of revision. So some revision questions. So why is it important that the resistance of an earth path is kept very low? So why is it important that we have a low resistance earth path? Yep. So basically, a low resistance path allows us to, gives us high fault current, which makes protective devices trip quickly. Yeah. Cool. So main earthing conductor. So it's the conductor that connects the main earthing bar, MEB, or earth bar in the switchboard to the earth electrode. That is what our earthing conductor is. So it provides essential low resistance path for earth for fault current. Typically runs from the main switchboard to the earth electrode. It can be a rod, a plate, or any other approved type. And the size is determined by 3000 based on the installation type. And it's the backbone of our protective earthing system. Without it, the MEN link has no return path. Yeah, so sometimes you can have an earth plate or an earth grid or an earth mat. Some of the generators have giant kind of mesh, almost fields of copper buried under the ground. And what tends to happen when they install them is they have to dig up the ground, they put down the copper mesh mat, and then they have to quickly bury it again because obviously giant field of copper, people are going to have a field day. So it's the most critical link in the chain. Think of the main earthing conductor as the motorway for fault current. Direct, low resistance, and always available. This is the missing or compromise. If this is missing or compromised, the MEN system doesn't work. So what happens in the event of a fault? We can have neutral return current flowing through the earth. Yeah, we're just having a review of the last topic, or at least parts of it. We're going to kind of breeze through it. Cool. So the earth electrode, it's our anchor to the earth in New Zealand. MEN system, it doesn't carry huge currents under normal conditions, but in a fault, it ensures the system remains bonded to the true earth potential. So it provides a physical connection to the earth, or what we call the general mass of the earth. It's installed outside the building, as close to the switchboard as we can. And the reason it needs to be outside is because it needs to be accessible for inspection. So if we put it under the house or under a concrete slab, it's not accessible for inspection. Yeah, it's a physical interface between our electrical system and the planet. Cool. So equipotential bonding conductors, it's about keeping everything at the same level. If two pipes are at different voltages during a fault, touching them could complete the circuit through you. So bonding straps need to tie the two pieces together so there's no potential difference. So when plumbers cut copper pipes under the house, so we didn't used to use earth stakes. We used to used to use the copper pipes as our earth. So you'll find that in old homes. And so what plumbers would do is they didn't realize there was current flowing through the earth. So they would cut the copper pipe, but then they would touch both sides of the copper pipe at once, becoming a conductor. So what they're supposed to do is take a 4 or 6 mil earth, strap it to either side of the bit of pipe that they're cutting, and then cut. So that way there is a continuous earth path that is not us. Yeah, it keeps, it ensures that all metal work is at the same potential, and in the event of a fault to a metal, a piece of external metal that's bonded, it'll create a path through the earth back to the earth bar through the MEN link to the neutral and allow our circuit protection to trip. Cool, it's the MEN link. It's the heart of our earthing system. It's what it's all based off. ever since 1929. It's what actually ties the neutral to the earth. And if it's loose, missing, or corroded, the whole protective system becomes unreliable. It's not that the protective system won't work, but it becomes unreliable. So it's installed at the main switchboard. It's usually a brass or copper link. Sometimes if the earth bars and earth and neutral bars are too far apart, we can use a piece of 6mm to go between the earth bar and the neutral bar, or an equivalent size to the main earthing conductor. Cool, in our main neutral, it's the main return highway for the installation. It's always carrying load current, and it ensures the neutral, the MEN link ensures the neutral is never floating. It's locked to the earth, potential for stability and safety. And then we have our protective earthing conductors. So think of these as the individual circuit safety line. The main earth bar is your hook on point, and the socket outlet you work at is you working at height. It's there to stop you from falling and dying. They run to each connection point and into the circuit. So just like a harness, it's going to stop you from dying. It's not going to be pleasant, but it will stop you from dying. So we run it with the active and neutral conductors in our cables. According to the wiring rules, it is supposed to be in the center of the cable. The reason for this is if you hit the cable from any one point, you're going to either hit neutral earth or phase earth. So you're always putting the earth in the middle to protect ourselves. And then we have functional earthing. So it's an electrical connection to ground that's necessary for the proper operation of equipment rather than for electrical safety. It provides a stable reference point and reduces interference in electronic systems like PLCs, data networks. And unlike a protective earthing conductor, it's not designed to handle fault current for safety, but rather improve signal quality and prevent malfunctions. And they're used for noise reduction, so it acts as a low impedance path for high frequency magnetic noise, preventing it from affecting sensitive electronic circuits. So does anyone use functional earthing in their day-to-day? Or has anyone played around with any functional earthing? I've only had to deal with it 2 times. It was once in the hospital connecting the data racks. The data racks needed a functional earth connection, so we had to run one back to the switchboard in the data cupboard room. And then once for an RCBO. Some RCBOs require a earth reference or functional earth. So most of the time we're talking about protective earthing, making it safe. But some equipment like electronics also need the functional earth, which is about performance rather than shock. So a protective earth conductor ensures safety by discharging faulty current. Functional earthing ensures correct operation, so electromagnetic circuit, EMC reduction and signal reference. Protective is mandatory for safety. Functional is something required by the equipment design. Cool. Disconnection times. So some of you guys were having a bit of trouble for this. So the reference for the cause is 3001.5.3D and 5.7.2. The maximum disconnection time for 230 400 volt supply voltage shall not exceed the following: 0.4 seconds for socket outlets rated below 63 amps, handheld class 1 equipment, portable equipment intended for manual movement, 5 seconds for other circuits, including sub-mains and final sub-circuits supplying fixed or stationary equipment where people are not exposed to unsafe touch voltages. So that 0.4 seconds refers to the close protection limit. So if you think about an RCBO, Normally, when we think about its disconnection time, we're thinking about the RCD side of things, which is 300 milliseconds at its rated current or 40 at 5 times. But because it also incorporates overcurrent protection or short circuit protection, it is allowed to trip at 400 milliseconds for the short circuit current. So when it's earth leakage, it's 300, but for a short circuit, it's allowed to trip in as much as 400 milliseconds. Cool. So here's a toaster with a solid earth. The breaker trips instantly. With a poor earth, the toaster still works, but the casing is live. But it is deadly. It's the same logic that applies in damp areas, except water makes things far greater. So low PEC resistance, high current. Low PEC, low current. Cool. So that's revision out of the way. Let's move into Unit Standard 32625, damp situation. So we're talking, taking that knowledge that we talked about earthing into damp situations. So when you're standing barefoot in a bathroom or by a pool, even a small voltage can be lethal. That's why AS/NZS 3000 gives us strict rules on zones, IP ratings, and bonding. Today, we'll start by looking at how damp zones are defined, and we'll talk a bit about the IP index and what that tells us, what equipment can safely be installed. And remember, don't use the toaster in the bathtub. Cool. So some definition. So it's defined as in 3000, a situation in which moisture is either permanently present, intermittently present to such an extent it'd be likely to impair the effectiveness or safety of an electrical installation that complies with this standard for ordinary situations. So ordinary situations. So we'll look at a few examples, but it's a situation isn't just water pouring directly onto the equipment. It includes condensation, steam, and splashing. Think of steam in a bathroom or a kitchen, or a kitchen bench near a sink. All of these reduce insulation strength and make shock more likely. Equipment in damp areas must protect people from shock. Water and humidity lower the resistance, so even small voltages are dangerous. It needs to resist water damage. Fittings must be designed and installed to withstand moisture. The general wiring rules still apply. These requirements are extra for damp situations. So, can anyone think of some common examples? What would you say is a common example of a damp situation? Yep, bathroom. Laundry, yep. Sauna, yep. Pool. Outside, yep. PowerPoint lights, pump shed, outdoor plugs, yep. A wash bay, 100%. Yep, spa. Yep, so those are some good ones. So the ones we've got listed as examples. So we've got your bathrooms and your showers. So sometimes you might not necessarily have a shower as part of a bathroom. It might be a separate standalone kind of area. Think about like the showers at the gym. Sometimes they're in a separate room, or at like a campground. Sometimes they're on their own and it's not really a bathroom, it's just a shower cubicle. Laundries, yeah, 100% laundries, steam, and you've also got laundry sinks. Kitchens, there's steam, there's water containers, especially if you've got taps that are extendable, and your swimming pools and your spas. So, what do all of these have in common? Yep, water. So all of these specific areas may contain a water container. That's a key term when we talk about dam situations, is they have water containers. But then you've also obviously got your outdoors, so your garden sockets, your exterior lighting. Has anyone ever installed what we call a holiday socket? Or has anyone heard the term holiday socket? So it's not too much of a common term here, but I have done a couple jobs for specific. There were a couple of them were American, but not just American, where they wanted a dedicated outlet for their Christmas lights. So they call it a holiday socket, or in the American, a holiday receptacle, because it's dedicated for their Christmas lights. So it's usually on the soffit up high where it's kind of awkward to get to, but it's there so they can plug in their Christmas lights. Yeah, some people, I mean, does everyone in where they're living have those people who get really hardcore around Christmas and put up all of the Christmas light decorations? Not sure yet. You? Oh, yeah, that's good. Want to see photos then, Sasha? Yeah, so one of the things I used to do when I was a kid, go around all of the local area, not in the country. Yeah, so yeah, as a kid, I'd be taking around all of the Christmas lights on Christmas Eve to the point where I'd fall asleep, and then, you know, my parents could do whatever they were doing for Christmas Day. Yeah, one day that'll be me, hopefully. Cool. So equipment in damp areas. So there's certain things that the equipment in these damp areas must do. They must protect people from shock. So water and humidity lower body resistance, so our own, and the resistance of any material. So even small voltages can be dangerous. So resist water damage. So they must be designed and installed to withstand moisture. They're normally, if it's designed for exterior, it will say it's designed for exterior. So the general wiring rules still apply. The requirements for damp situations are extra for damp areas. So where they apply, so we talked about bathrooms, showers, pools, spas, and paddling pools, fountains and water features, saunas, refrigeration rooms, areas that get hosed down or sanitized. So what would we class as a water feature? A fountain? Fontaine? Ooh. Sprinklers? Yeah, they can be classed as a water feature because they spray water. What about a bidet? Would you class that as a water feature? Pond? I'd call that a paddling pool or a pool, the pond. But what about a bidet? Would we class that as a water feature? So a bidet or Japanese toilet is a toilet that instead of you using toilet paper, it uses a jet of water to clean your sensitive areas. Fair, fair. Yeah. Thailand special. Okay, Case. Yeah. So yeah, I would tend to class it as one. And so when I get asked to put, and it does seem to be in people from a similar area to what Case is talking about, it seems to be people who are from that area who want to put in these bidet toilet seats. And so we have to provide a power socket for it. And so we have to follow the rules of the damp situations, as well as making sure that it's out of the squirting radius of the water feature. Cool. Is this safe? Yeah, the amount of times I've seen this image on the internet, I'm pretty sure this has been around since the days of Bebo. And I'm wondering if anyone's old enough to remember Bebo. Or is it just, no, it can't just be me. I'm sure some of you guys remember Bebo. Cool. So why damp situations equal risk? So when your skin is wet, its resistance. Yeah, so when your skin is wet, its resistance drops drastically. It means much smaller voltage can give you a lethal shock. Combine that with damaged insulation from dampness, and it's clear why these areas get special rules. So, water conducts electricity, especially with salts and minerals. So, the tap water we drink is never 100% clean unless we use a filter, and even then, there's probably still something on the inside of the pipe that was installed however many years ago. And even if it was clean, there's always going to be something that gets through. So there's usually something in the water. I mean, most people who live in a central city, maybe not necessarily out in the country, have chlorine in the water to some degree and fluoride to help treat it and maintain the basically for sanitary reasons. But obviously, that does make it more conductive than if it was pure water. So the dampness lowers our insulation resistance. So if a cable is damp, what you can actually do is you can insulation resistance test it. You can leave it on, say, 500 volts for an extended period, and it can actually dry out the cable. It is not recommended if you can replace it. But yeah, it would, it can clean out waterlogged cables, especially if it's been in a conduit that's flooded. Cool. So you get an increased risk of electric shock because of our reduced body resistance when it's wet. So fire, equipment damaged by the moisture, potentially arcing. And then, is this a damp situation? So, damp situation. Yeah, definitely. It's a bathroom. There's the shower, the sink, possibly a bathtub. There's a lot of areas we need to be aware of. So it's definitely a damp situation. Definitely tick. Bedroom. Yeah, depends if they have a bidet in there. Unless Wellington flat, then yes. Yeah, to be fair, yeah, Wellington flats are fair enough, but it is not deemed to be a damp situation unless there are external factors and someone's done something silly. Cool. Kitchen. Yeah. So sink, it depends. Yes, but it depends on the proximity to the water source. So as we move away from the sink and away from the tap, it becomes less of a damp situation. So in a bathroom, the whole thing is considered usually to be a damp situation. And we'll look more about later on zones and measurements. But again, it depends on how close. Cool. The spa or the outdoor pool. Yep, 100%. A spa or an outdoor pool is going to be a damp situation. So we need to be careful about where we put our isolators and where we put our any outdoor receptacles or power points. Does anyone who installs outdoor power points allow for drainage? Yeah, drainage in the isolator. Yeah. A T in the lowest point. Yep. Yeah, tiny hole. So try and make it small enough that insects can't get in, but that water can get out. The other option is if you're bringing a conduit into the isolator, you bring the conduit down and then you bring it up, and then you can make a very tiny slit in that corrugated conduit, and water can drip out that way. It also creates a water lock if you do it properly. Yeah, you have to be very careful not to ruin the IP rating if you draw them out. Ideally, they won't get water in them if they're sealed properly, but you should always make sure. Generally, I don't drill a hole in the bottom unless I know there's going to be rain, to like driving rain. Usually, I try to hide my isolators, but I always, before I put the isolator on, silicon behind the isolator. So I do what's called back buttering the isolator, cover it with silicon, put that against the wall, screw it, put a small dab of silicon over the screws, use the included caps to cover those screws that are in the isolator, and then make sure that the seal that I've got for the isolator is in good condition. If all those things are done, and then you put the caps on the outside of the isolator, if that in any way gets water into it, then it's kind of almost a manufacturer's fault, and I would be going back. Yes, I glue the bungs. Yeah, I glue the bungs, so the bungs in the side of the isolator, pop them out, little bit of conduit glue back in, because you've got to make sure you do everything possible to make sure no water gets in there, because you don't want to have to come back and then tell the customer, oh, you got water in there, especially if it's only a year after you installed the thing. Yeah, so we've got to be very careful when it comes to moisture ingress and water ingress. Cool. So our next example, the garage workshop. Is this a damp situation, a garage workshop? All right, so you make it very hard not to. Yeah, got it a bit. Tim, it's a good one. Yeah, so we would generally consider the garage workshop not to be a damp situation, but again, it's if there are other factors. So if that garage workshop shares its space with the laundry tub and the washing machine dryer, like a lot of modern Wellington homes do, or does it have a wash-up sink in the corner? Is there a reel up hose wheel inside the garage that you can then pull outside the garage door to water your garden? All of these things are factors we take into account, but as a general rule, it's not classed as a damp situation until we add the laundry, until we add the wash up sink. Cool. This would be, looks like a cattle shed. Would that be a milking shed? Yeah, I can see the water on the floor. I will wholeheartedly admit I am a city and kind of suburb guy, and I have only been to a cattle farm twice, and only once did I see the milk shed, and it was one of the round ones, so I have no frame of reference. But yes, we would consider this a wash down area because it is going to be hosed regularly, probably because of all the poop. Cool. So some key takeaways from what we've talked about so far. Dam situations equal environments where water or moisture can compromise electrical safety. It's not limited to the obvious, like showers. It includes any space where water is present or likely. So these areas require extra precautions, so IP-rated fittings, RCDs, bonding, or safety extra low voltage or protective extra low voltage. So these are the kind of things we need to take into consideration when we're looking at dam areas. Does anyone have any questions about things we've covered so far that aren't related to bidets? Safety extra low voltage. So safety extra low voltage is like your 24 volt. So that would be like your garden lighting. PELV. I'm trying to remember the exact number. So protected extra low voltage. So it's where the secondary winding of the transformer is earthed. So it's basically protected by a transformer. Okay, so we'll move on to the IP index. So the IP index is the degree of protection of an item of enclosed equipment is expressed as an IP international protection rating in accordance with AS 60529. That's a quote from AS/NZS 3000, 2007, Appendix G. So it's a measure of the level of protection an enclosure affords a piece of electrical equipment from solid and liquid matter. So the first number from 1 to 6 designates a degree of protection against solid objects and protection of persons against access to hazardous parts. But not just solid objects, but also people. So the second number from 1 to 8 designates a dress of protection against entry of water with harmful effects. So if a specific degree of protection is not designated, an X is used instead of both numbers. So when you see IP44 stamped on a light fitting, it's not just random. The first 4 tells you how well it resists dust or solid objects. And the second 4 tells you how well it resists water. Every digit has a meaning, and that's how we choose the right gear for damp areas. So when you see an X on the IP code, it doesn't mean zero protection. It just means that part of the test wasn't carried out or declared. So it very well may meet one of the numbers, but they just either didn't test it or they didn't declare it. So, for example, IPX4 means we don't know about solids, but it is splash proof against water. That's why in bathrooms we often see IPX4. We only care about water and not dust in the bathroom. Does that make sense? So yeah, some people use, instead of saying IP means international protection, they use it as ingress protection, as in the protection against the ingress of solids and water. But the appropriate term is international protection. According to AS 60529, AS 10ZS 3000, 2007. I think they will just use it as IP. And if you use ingress or international protection, and it's one of the answers that you have to write it out. So you'll be given a multi-choice question, and I don't think you'll be asked, is it ingress or is it international? And if it's one of the written questions in the assessment, I'm the one marking it, and I know the terms can be used interchangeably. Like, for example, the next page we're going to look at. So this, it says ingress protection. See, they are used interchangeably. Cool. So let's break down the digits. So the first digit of solids, 0 is no protection. 1 is large objects bigger than 50 millimeter diameter. The 2 is fingers or more than 12 millimeter. 3, screwdrivers, more than 2.5 millimeter. 4 is wires or tools, more than 1 millimeter. 5 is dust protected. 6 is dust tight. So those are what those numbers mean. So from 0 to 6, they are different meanings. And obviously this poster is not very clear because it's not, I mean, I can barely read it and I'm sitting right next to the projector. But you can find these on the internet. Basically, number 1, I can stick my hand in it. Number 2, I can stick my finger in it. Number 3, I can stick my screwdriver. Yeah. And it just gets more and more robust. Let's break down the other digits. So the second digit is for water. So 0 equals no protection. 1 is protected against vertical drips only. 2 is protected for drips up to 15. Yeah. If it helps, guys, you can use the function print screen option on your computer and it will take a screenshot. I know, obviously, if people want to write it down or they're taking manual notes, that's how I learn better. Yeah, I personally learn better when I write things out. But again, recording will go straight onto YouTube. I probably won't go home after this. I'll probably stick it on YouTube before I go home. Let's choose that. Yeah. Sweet. So let's look at the water. So drips up to 15 degrees from vertical. So if this is vertical, it's about, kind of here. The problem is I can't stick my arm too far down, otherwise I get in trouble. I get to the wrong degree. I'm hoping everyone got that joke. Cool. 3, spraying water. So 60 degrees from vertical. Yeah, basically, Sasha, yeah. Thank you, Daniel. Yeah, so yeah, spraying water up to 60 degrees from vertical. Cool, and then 4 is splashing water from all directions. So you see, which went from 1 it drips, 2 it drips, 3 spraying, 4 splashing. Then at 5, we're protected against water jets. So that's water moving at force. And then 6, water from powerful jets. So that's your thing like, so the water jets would be like water kind of almost waves, whereas water jets would be your water blaster or the water coming out of your hose. 7 is immersion up to 1 meter for 30 minutes. So it can stay underwater up to 1 meter for 30 minutes. And then 8 is for continuous immersion. So a socket marked IP20 is finger safe, but it's useless against splashes. And we compare that to IP67, which can survive full immersion in a meter of water. That's why we can't just throw in any fitting. The rating has to suit the location. So when we buy a light fitting and it's IP44, we think it's safe to stick in a damp area? Yes. But if that damp area is going to be subjected to washdown, we must have at least a IPX6, or I would go with an IP67. Just to have that one level above the water from powerful jets. So has anyone done any installs in washdown areas or where they had to use anything up to an IP 67? The data, yep. Still counts. Has anyone had to do a 68 fitting? Tesla Powerwall? Oh, yep. Can anyone think of where they might need an IP68 fitting or a common IP68 fitting? A boat? Yep. A spa? Yep. And the fitting inside the spa? Yep. Sub pump? Yep. The only one I've had to do, and we had to drain it to do it, was 20 lights in a pool at a house in was it Moonshine Valley Road? The one that goes over from between Porirua and Lower Hutt. One of the nice big flash houses around there. We had to drain this lady's pool and replace all of the underwater lights. Yeah, someone had installed a bunch of 67 fittings, and they lasted for about 2 years, and then they finally gave out, and then we had to replace them with IP68. So we always need to make sure that we use the correct fitting for the situation. Cool, so maintenance and compliance. So IP ratings must be maintained. Broken seals, missing covers, and wrong replacement parts equals reduced rating. Always replace with parts rated for the damp situation. So an outdoor socket with cracked gasket is no longer IP44. If you swap a light fitting seal with a cheap part, you might have just turned an IP44 fitting into an IP20. It might look fine, but it's no longer compliant, which is why most of the time, unless it's a extremely expensive light fitting or it's a one-off fitting, most of the time you will just replace the fitting. It is often cheaper and more cost effective to replace the entire fitting and prolong the life of that fitting. Cool, so the IP index. So this socket is usually used outdoor and it's IP53. So it's dust protected and water up to 60 drips up to 60 degrees vertical. So it is normally installed outside. So this is commonly your outdoor power point for your garden lights, for your power tools. Some people, it's not good practice, but some people install these for your outdoor infinity. But can anyone tell me why this might be a bad idea for your outdoor infinity? Yeah. Someone can turn it off or someone can unplug it. Driving rain, because of the way the socket is angled, it's not too much of a big deal. Cleaning the house, yeah. So basically, someone can literally just unplug and run off with your outdoor, we'll call it a Califon. If they shut off the water to it and shut off the gas, they can just unplug it, cut the pipes, and run away. It's much harder to do that if it's hardwired in, but at the same time, they could just turn off the switch and cut the cable. Cool. So dust protected, heavy jets from all angles. One thing you can do if you don't want people to turn off your hot water is you can use a lockable isolator and you can lock it in the on position. So most PDL 56 series isolators, you can lock them in the on position. So the reason you might do this is for things like your outdoor hot water units or for your heat pumps. You can lock it in the on position so people can't screw with your power or screw with your heating or your hot water. Cool. So we've got a couple lovely light fittings here. So this plastic ball one is IP44. It's protected from solid objects up to 1 millimeter and splashes from all angles. Whereas this one is an IP65 glass. So jets of water from all angles and it is dust tight. If you have any of these light fittings and you're replacing them, make sure if the ball or the cover is in good working order, you hang on to them and keep them in a safe place. They are becoming very hard to come by, and so people are willing to pay a lot of money for them. I've got a glass version of the one on the left at my house, and when I replace that thing is going into bubble wrap and into a box. Cool. And then we have our switchboards. So IP40, solid objects up to 1 millimeter, no water protection, definitely not allowed in a bathroom. IP56, dust protected, heavy jets from all angles, still not allowed in a bathroom. Does anyone know why I'm putting such an emphasis on that, not allowed in a bathroom? Yep, Sean's on the right track. A bathroom is a restricted area that is not allowed to have a switchboard in it. However, when people do up their houses, they take the switchboard that used to be in the laundry, which was legal back in the days, and they turn the laundry into a bathroom. All of a sudden, I have a switchboard in the bathroom. Obviously, they didn't have any electrician come through when they did this work, because the electrician would have taken one look and gone, maybe I should put that on the other side of the wall. So if you come across a job like that, you can just take the switchboard, move it to the other side of the wall, even if it is the outside of the building. As long as it's within, the main switch is within 2 meters of the floor, then it's okay. But yeah, never a bathroom, never a laundry. My preference, outside, in the hallway, in the garage. Probably hallway, then outside, then garage. And preferably as close to the kitchen as possible because that's going to be my 6 mil for my cooker. Cool, so where they apply. So according to AS/NZS 3000, 2007, in section 6, which is damp situations, we have 6.2, which covers baths, showers, and fixed water containers. 6.3 is spas, pools, and tubs. 6.4 is fountains and water features. 6.5 is saunas. 6.6 is refrigeration rooms. And 6.7 is hose down and sanitation areas. These areas don't have zones. We'll talk about those in a little bit, but have specific rules around electrical installations in these areas. Cool. So this week we'll cover 6.2. Next week we'll go from 6.3 to 6.7. So they're broken down into zones which set the boundaries around water sources. So the zones determine what equipment can be installed and the minimum IP ratings required and any extra installation rules. So they're broken down into these areas. So 6.5 saunas and any other damp areas, they're not zoned. So we'll look at the zones around baths, showers, and fixed water containers. And then next lesson, Paul's back to it. So that's what we're going to cover over tonight. We're going to start with 6.2, and then next week we'll go into detail in the other section. So zones, baths, showers, and fixed water containers. So zone 0 is where the water is. So it's inside the bath, shower, spa, or pool, anywhere fully exposed to water. So zone 0 is the surface of and inside of the water. Cool. Zone 1, the area above zone 0, up to 2.25 meters vertically. So vertically and directly surrounding a bath or shower. So basically from the water up to a height of 2.25 meters vertically. Why 2.25 meters? Why do you think it's a height of 2.25 meters? Splash, yep. Ceiling height plays into it. Your standard ceiling in New Zealand is about 2.4 meters from the ground. Condensation. People height, yeah. So 2.25 meters is the safe out of touch distance. So it is a distance where it is considered safe from someone being able to reach it. So, for example, if I'm standing at the ground and there's a wire above 2.25 meters, it is considered safely out of reach of me unless I was to grab a ladder. So that's another part of 3000, but basically if there's a platform permanently affixed in an area, we take it from the height of that and up. So if we've got a bath and it's, yeah, I know if you're tall, but it's what we define in 3000 as safe out of touch. Again, it's the number that they decided upon. Probably they took average height people at the time they wrote it, and that's what they went with. But then as we move from zone 1 to zone 2, so the area stretching 0.6 meters horizontally beyond zone 1 up to 2.25 meters. So it's basically 0.6 meters away or 600 mil away from the rim of the bath or the entry into the shower. So, and again, still up to 2.25 meters vertically. So that height doesn't change. And then we have the area stretching in zone 3, the area stretching 2.4 meters horizontally beyond zone 2 up to a height of 2.25 meters vertically. So the zones reach up to 3 meters away from the edge of the water container. Now, I don't know about the rest of you, but I don't think my bathroom is bigger than 3 meters at my house. Does anyone think they've got a bigger than 3 meter bathroom? Yeah, I don't see the point in having a bathroom that's bigger than 3 meters. I'm pretty sure some of the bathrooms in the flats in Wellington are less than 2 meters square. So zones are just a way of mapping out how close equipment is to water. The closer we get, the stricter the protection needs to be. And zone 0 is literally where the water is. Zone 1 is a splash zone. Zone 2 is the mist and damp area around it. So that is what we consider the zones. So do you think, so in the picture, the orange surface on the shower or on the surface of the water is zone 0. Zone 1 is the orange leading up to the ceiling. Zone 2 is the green area, and zone 3 is the blue. Now, if you give me a sec, the picture here in this slide, I think that paints a little bit better of a picture. So it's a bit easier for us to understand when we talk about zone 0, 1, 2, and 3. So we've got zone 0 is the bathtub itself. Zone 1 is directly above the water of the bathtub. Zone 2 being that 0.6 meters from the edge of the water to a height of 2.25 meters. And then zone 3 being a further 2.4 meters beyond that. So if we didn't have zones, every bathroom would be guesswork. No, it's to the door because it can be shut. Yes, it would be nice if they used color in the 3000, but when they designed the book, they figured they'd wanted to use colors that saved on ink. So they could print it in black and white and it would still work. That's why they do the way they do in 3000, because printing in color. I think there are some people out there who have taken PDF copies of 3000 and edited them so these pictures are in there instead. But because they're technically not official documents, well, you can use them, but you just can't reference them, if that makes sense. You just can't use them in an official capacity. Cool. So why do we use the zones? So it stops us from having to do guesswork. It gives us exact boundaries so we can match fittings, IP ratings, and the protective devices. So risk level increases the closer you are to the water, and it makes the rules consistent and easy to apply. And it prevents dangerous fittings being installed too close to baths, showers, or basins. So do you think I can install a PowerPoint, a standard normal PowerPoint in zone 2? Without looking at 3000, yeah. It's not a good idea. So there are rules around, and it is in 3000. You guys will be reading about it as you do the SCORM packets on LMS. Cool. So if we didn't, I already said that. So these are the actual pictures that you have in 3000. So if you look at them, this is figures 6.1 and 6.2. So 6.1 is a top-down view of a bathtub inside of a bathroom. Now, this is a pretty big bathroom, but it's obviously there to give us a good reference picture. And then zone 6.2 is the same, except a vertical. Now, if you notice here on 6.2, you have the Australian, you have an A and an NZ next to two different numbers. So in Australia, they go 2.4 for zone 1. And in New Zealand, for zone 1, we go to 2.25. So in New Zealand, it's from the floor. or at least that's what the picture would make us believe. So, to make it a bit clearer, zone 0 is highlighted in red. Zone 1 is highlighted in orange. Zone 2 highlighted in green. And then zone 3 highlighted in blue. So these are the zones. And depending on the zone, there are specific rules in 6.1 and 6.2 as to what we can stick where. So for this, so to really understand how zones work, we'll look at one particular example straight out of AS/NZS 3000. It shows us the dimensions of the zones around a bath or shower, so you can actually see the zone. Once we've got the visual in our head, table 6.1 will tell us the types of fittings and equipment allowed in each zone. So you'll see in zone 0, it's very restrictive, while zone 2 gives us more options. So after we've looked how to go at that, we'll look at some other common bathroom layouts, showers without trays, basins, corner baths, etc. So we can see how the zones change depending on the situation. This way, you won't be just memorize the numbers, you'll be able to apply them to any bathroom you come across. So here's an example, shower without barriers. So we'll go back, table 6.1. Might just quickly pull up my PDF copy of 3000. Table 6.2. Cool. This is table 6.2. So guidance on the selection and installation of electrical equipment for, never mind, it's table 6.1, isn't it? That we want. You can see in AS/NZS 3000, there's a lot of fun pictures for damp situations. So yeah, 6.1. So if we look at zone 0, for socket outlets, not permitted. Switches and accessories, not permitted. Luminaires, IPX7, and specifically for use and safety extra low voltage or protected extra low voltage supply. And anything else? Only on IPX7, SELV or PLV supply. And of course, switchboards, not permitted in any zone. Then when we get into zone 1, it's not permitted to have any socket outlets. When it talks about switches and accessories, it talks about zone 2. Then luminaires and other, it has to be IPX4. Cool. Zone 2 must be a shaver outlet or RCD protected and in a cupboard with no specific IP rating. So has anyone seen the old shaver sockets? Can anyone hazard a guess as to why they would be allowed that close? I've used one of them. Yeah, they have a transformer on them. So that is why they're allowed to be used. They are protected extra low voltage. So for switches, more than 0.3 meters not permitted. Sorry, less than 0.3 meters not permitted. And then equal to or less, more than 0.3 meters can be IPX4. So IP for luminaires, IPX4 or Class 2 construction, double insulated, double or reinforced insulation, or again, SE or PELV, or recessed into the ceiling. So the majority of the light fitting is in the ceiling, but we can get IP rated downlights. And again, for anything else apart from switchboard, IPX4 or recessed into the ceiling. So that would be for things like I have seen them installed, the sound system inside of the bathroom, so you can rock out to tunes while you're doing your business or having a shower. And then for socket outlets in zone 3, so that's more than 600 away from the water container, cannot be within 0.3 meters, must be equal to or more than 0.3 meters, but no IP rating, but shall have RCD protection or separated supply or SELV or PLV supply. When it talks about the 3 meters, it's talking about height from the floor. Cool. So luminaires no longer need IP rating in zone 3. Anything else does not need IP rating in zone 3, but again, switchboards are not allowed. And a degree of protection of IPX5 is required in communal baths or showers in zone 1 and 2. Or any zone 1, 2, and 3. So IPX5 is required for communal baths and showers. So knowing that, so this is figure 6.3 and 6.4. So this is shower with base without barriers, so an open shower. So we have zone 0 is pretty small because it is just the water container. But if you notice, zone 1 extends out 1.2 meters from the fixed shower plumbing connection. So basically 1.2 meters from the shower head. Does that make sense? So basically what they're saying is most of the time a fixed shower head can spray out to 1.2 meters. And then again, still 2.25 for New Zealand, 2.5 for Australia. Zone 2 is still, we will get to that. So yeah, then zone 1, zone 2 is still 6 meters, sorry, 0.6 meters away from zone 1. And then zone 2, 2.4 meters out from zone 3 is 2.4 meters out from zone 3. And then, so that is reflected both in the vertical and the horizontal. So whenever they give you an example in 3000, they will give you both a vertical and a horizontal picture to work off of. Because if you don't have the horizontal reference looking at the vertical, it's not quite as easy to tell, whereas a horizontal will not give you the vertical measurements you need. Cool. So this is for a bath without a fixed barrier. So for this, we're being given the top down, so zone 0 and zone 1 being the bathtub itself, zone 2 being 0.6 meters. So it's with a fixed barrier. So zone 2 extends 0.6 meters away from the wall to where the barrier is. But if you notice, do I have? Yeah. There is it does, come on, work. I've got it on the eraser. There is a kind of curve here because it gets to this partition here, and then it curves around in a circle on that point. So it uses the end of the partition wall as the pivot point for the zone, and that's where zone 2 ends. And then, of course, zone 3 is 2.4 meters out from that, and there is that slight back curvature down the bottom here as well. So that's what happens if you have a fixed barrier on your bathtub. Cool. So this is a bath.
Can you hear me, Stu?
Yep.
Quick question, mate. I'm just reading the figures 6.5. It says bath and showers, zone dimensions, bath without shower and fixed barrier. And then figure 6.1, it literally references the same bath without shower or fixed barrier. So what are the key differences between 6.5 and 6.1? The diagrams are different.
So 6.1, we go back to it, is bathtub with no barrier. So it's a bathtub without a shower head, without a barrier. And then if we go to 6.5, it has no shower, but it has this fixed barrier at the end here. So it changes the dimensions of zone 2. So it has a curved area around the end of the barrier. So we can use that corner of the barrier as a pivot point to draw out our zone 2.
Oh, gotcha.
So yeah, the first one is just the bathtub, open, no barrier, no knee wall at the end of the bathtub, no nothing.
It's not very clear that they don't really indicate that A is the yeah. Anyway, that makes sense. So they start with just the standard bathtub and shower, and then they add the barrier, and then they add a shower head, and then they add like a movable water head as well as you get further down the units. So it starts with the basic and then gets complex from there. So we go to 6.6. It's bath with a shower without a fixed barrier. So as you can see, zone 0 is the bathtub water itself, as well as this 1.2 meter radius from the fixed shower plumbing connection. And then zone 2 must move to be 0.6 away from all of these different areas in zone 1. So yeah, zone 0 is the water and itself, zone 1 being 1.2 meters zone, out from the shower head, and then the bathtub water up to a height of 2.25 meters. Zone 2 being 0.6 meters from the edge of zone 1. Zone 2 being 0.6 meters from the zone 1 up to 2.25 meters. And then again, zone 3 being 2.4 meters beyond zone 2 up to a height of 2.25 meters. So, is anyone confused on anything we've talked about so far? It is quite a big topic, but it's kind of, once you get the hang of one and you read over it a few times, it starts to make sense. Basically, all it's telling us is basically anywhere from zone 1 to zone 2, I'm not really going to put anything. Zone 3 is where I'm going to probably comfortably put an RCD protected socket or my light switches. But anything too close to the shower or the bathtub, no dice. Cool. And then we go to an enclosed shower. So it's enclosed, but it has a door. So zone 0 is our bathtub pan. Zone 1 is the area above it. And then zone 2 is 0.6 meters directly out from where the door is. And then using the pivot pinch point of where the door is, we use that as our pivot point to create another 0.6 meters for the barrier. So similar to the way they did for the bathtub, where the fixed barrier or the fixed part of the enclosure ends is where we draw our 0.6 meters and use it as our the center point of our compass, basically. So basically where the door opens, 0.6 meters out from that, where the pivot point on the door is, 0.6 meters in a radius around that. And then we just draw our zone 3 to match that as well. So that's figure 6.7 and 6.8. So the vertical is pretty straightforward. If we look at it from the side, it's once we look at the horizontal that we know that there is this kind of radius point from where the inside of the door is or where the door opens or hinges from. I think you have to draw one picture from the assessment. From when I was looking through it, I saw one point where you have to drop a file in. The rest is all description based. Cool. And then we talk about 6.9, a partially enclosed shower. So again, the fixed shower point, we have a 1.2 line until it hits the corner of our partially enclosed shower. That's where you can see there's this kind of line here and it stops there. There you go. I'll draw it in a different color. So you got this area here. That is our zone 1, and because it hits this wall here, it changes trajectory and gets cut off. Then we can change our zone 2, which is 0.6 meters from zone 1. It follows that same kind of hard line. Is that a little bit easy to see with the colors on the digital whiteboard? There we go. Yeah, sweet. I can make them a little bit chunkier. Just to really emphasize what's going on. Yeah. Almost looks a bit cartoonish there. Might go one size smaller for the next one. So this is what happens when we have a partially enclosed shower. Once we start moving into a movable shower head, we still reference it from the fixed plumbing connection. So if we have a movable shower head, as far as 3000 is concerned, nothing really changes because it's from the fixed plumbing connection point. I mean, realistically, it is a judgment call. If I see that there's a shower with a movable head, I'm going to maybe go a bit further than my zones. But again, at the end of the day, this stuff is all the minimum standard. So anything you choose to go beyond this is even better. So the minimum standard says I can put my light switch or socket outlet over here. But I mean, realistically, that's too close for me to be comfortable. I'm going to go at least out here on the edge of the zone. Or preferably, it's a bathroom. What do you need a socket outlet for? Maybe to charge your toothbrush. Cool. I'm going to make sure you have a medicine cabinet, and I'm going to put my socket outlet inside the medicine cabinet. Fair enough, Sasha. I don't have long enough here to think about that kind of thing. But you're 100% right. For a hair straightener, for hair dryer. But again, we can stick the socket outlet inside the medicine cabinet so that when it's in, like you're using the shower, there's a barrier between the outlet and the socket outlet. Or at least you have to open a cupboard before you get to the socket outlet. But that's just the way I would do it if I was doing a bathroom. Then we move into fixed water containers. So here we have a double water container, and here we have a single water container. What is plug-in heaters? Well, they're generally up high above the door, right? Those Serene fire starters, do we call them? I hope everyone gets the joke. Yeah, so if everyone remembers, there's still a whole bunch of those Serene heaters out there in the wild. Yeah, you've swapped out a couple, but there's probably still about 30% of them still out there just waiting for something to go wrong. So yeah, the difference between these two, and it's listed, so the fixed water container on the left is less than 45 litres. The fixed water container on the right is more than 45 litres. So that 45 litre mark is where the legal measurements change. So below 45 litres, zone 0 is the water. Zone 1 is still directly above the water, but zone 2 is only 0.15 metres and 0.4 metres above. So zone 1 is the surface of the water up to 0.4 metres. The zone 2 is 0.15 metre away from the edge of the water and 0.4 metres up. And there's only zone 1 and 2. There's no zone 3 for this. But then if we move over to the 45 litre and above, it should say equal to or more than 45 litres. We have to be 1 metre above the surface of the water before we're in zone 2. And we must be at least 500 away before we're in zone 2. The total amount of water held in one container. So not both of the containers, one container. Because if you look at those, they're both about the same overall size, but that one's divided in two. The reason for this is because if we hit the surface of the water and the one that's less than 45 litres, the splash could not be as large as if we splashed in the 45 litre or more. So it's all about how far the water could splash out. Yeah. So yeah, when we have less than 45 litres, we can get closer. If we have more than 45 litres, we have to be further away. But in my personal viewpoint, I ignore this one. Yes, amen to that, Sean. So I would never follow this measurement. I would be more comfortable with this, but my preference for a PowerPoint or a light switch near a water container of this size, I want to probably be at least 750 or more away from the water container. Again,
This is the minimum safe distance as per 3,000, but you can go beyond that. It is all about how far you're willing to go to make it safer. You know, yes, you can do this. If the client asks you to put a socket outlet, 300 above the bench, 0.6 meters away from the water container, legally you can do it. But what I would be telling them is, yes, I can put it that close, but do you really want it that close to the water when something might splash out of there? Who knows? Maybe they've got a small dog and they're going to use this sink to wash that small dog. And if anyone's seen any of those dog washing videos on YouTube, they can get pretty feisty, the small ones, and they love to shake. So that is... Please no toaster bathtubs. Cool. So that is the end of our teaching material. So I am just going to